So today we will going to discuss some problems related to most powerful test. Okay, here the question is given a random sample of size n from normal with mean mu and variance sigma naught square distribution and construct most powerful test for testing h naught mu equal to mu naught versus h1 mu equal to mu 1 where mu 1 is greater than mu naught. So here we want to construct most powerful test, right? So from the lemma we know that there are some condition, right? If a test is said to be most powerful, then it should satisfy two condition. The first one is size equal to alpha, and also the test of the form like 1 if f1 of x is the form 1 if f1 of x is greater than k into f naught of x 0 otherwise, right? There are these two conditions should satisfies, right? Then phi of x is to be most powerful test. So here we want to construct the most powerful test for testing h naught versus h1, right? So we will construct the most powerful test. Here we know that it's a random sample from normal with mean mu and variance sigma naught square distribution, right? Here it's also given that h naught mu equal to mu naught and also h1 mu equal to mu 1. Then here h naught, we can write h naught as x follows normal with mean here mu equal to mu naught, right? Under h naught mu equal to mu naught. Then here normal with mean mu naught variance sigma naught square versus what's h1 then? X follows normal with mean here h1 mu equal to mu 1, right? That is mu 1 sigma naught square, right? From Neyman-Pearson lemma, from Neyman-Pearson lemma, we know that from this test function we can say how to reject null hypothesis. So we reject a null hypothesis if f1 of x is greater than k f naught of x in the probability 1, right? Then this is the rejection region, right? So we can write these term as f1 of x is divided by f naught of x greater than k, right? So for the large ratio we can reject h naught with probability 1, right? That is from Neyman-Pearson lemma we know that we reject the null hypothesis for large ratio, that is f1 of x divided by f naught of x is greater than k. Okay, from the Neyman-Pearson lemma we reject the null hypothesis for the large ratio, that is f1 of x divided by f naught of x greater than k. So in this problem is given that it's a random sample of size n from normal distribution, right? So we want to take likelihood function, right? If x is a size 1 a random sample from size 1 from the normal distribution, then we can take f1 of x divided by f naught of x. But in the question is given that is size of n, right? So we have to take likelihood function. So what is the likelihood when under h naught? We know that under h naught x follows normal with mean mu naught variance sigma naught square. That is likelihood of what is f of x then? F of x mu naught sigma naught square equal to 1 by square root of 2 pi 1 by square root of sigma naught square e power minus 1 by 2 x minus mu naught whole square divided by sigma naught square, right? This is f of x under h naught for the case of single random variable, right? But here is given that is a random sample of size n, so we can take likelihood function. It is likelihood mu naught sigma naught square x1 x2 so on n size, right? That is xn, which is equal to the product of I 1 to n fx I mu naught sigma naught square, right? That is equal to product I 1 to n 1 by square root of 2 pi 1 by square root of sigma naught square e power minus 1 by 2 xi minus mu naught whole square divided by sigma naught square, right? Then you can write this product term as equal to 1 by square root of 2 pi power n, right? This product of 1 by square root of 2 pi is 1 by square root of 2 pi power n, right? Then here second term 1 by square root of sigma naught square whole power n, right? Then what is this term? Product of this term is equal to e power minus 1 by 2 summation I 1 to n xi minus mu naught whole square divided by sigma naught square, right? We can write this term as 1 by 2 pi power here square root of, right? Then we can take that square root outside, that is n by 2, and here also square root, right? Then you can write it as 1 by sigma naught square power n by 2, then e power minus 1 by 2 summation here sigma naught square, we can take sigma naught square here, sigma naught square I 1 to n xi minus mu naught whole square, right? Similarly, under alternative hypothesis, that is h1 x follows normal with mean mu1 and sigma naught square, right? Then what is likelihood? Then likelihood of mu1 sigma naught square x1 x2 so on xn equal to 1 by 2 pi power n by 2 1 by sigma naught square power n by 2 e power minus 1 by 2 sigma naught square summation I 1 to n xi minus mu 1 square, right? Here mu 1 square. Then we know that what is a rejection region here? A rejection region means the large ratio, right? That is in common case if it's a single random variable, then rejection region is f1 of x divided by f naught of x is greater than k from Neyman-Pearson lemma, right? But in the case here it's a random sample of size n, right? So we can write this as a likelihood term. That is here rejection region is likelihood of mu1 here f1 of x, right? Which means the density on the alternative hypothesis, here density on the null hypothesis. So in this case here likelihood on the alternative hypothesis, that is likelihood of mu1 sigma naught square x1 x2 so on xn divided by likelihood of under h naught, that is likelihood of mu naught sigma naught square x1 x2 so on xn, which is greater than k, right? That means we reject h naught for the large ratio, for this ratio. Okay, then we will substitute the value of likelihood. What's the value then? Likelihood of mu1 sigma naught square x1 x2 etc. so on. Xn is, what is that, this value, right? That is 1 by 2 pi power n by 2 sorry, then 1 by sigma naught square power n by 2 e power 1 by 2 sigma naught square summation I 1 to n xi minus mu1 whole square, right? Divided by likelihood under S naught, that is 1 by 2 pi power n by 2 1 by sigma naught square power n by 2 e power 1 by 2 sigma naught square summation I 1 to n xi minus mu naught whole square, which is greater than k. You can take this as k1. Okay, here you can take it as k1. Then these terms got cancelled, right? Which implies, what is the remaining terms? That is e power minus 1 by 2 sigma naught square summation I 1 to n xi minus mu1 whole square divided by e power minus 1 by 2 sigma naught square summation I 1 to n xi minus mu naught whole square, which is greater than k1. Okay, and then we will rearrange this term. That is, we can write this term as 1 by e power minus 1 by 2 sigma naught square into this term summation I 1 to n xi minus mu1 whole square. So we can take this term here. Then this is minus this term, that is summation I 1 to n xi minus mu naught whole square, right? We can write these term together, that is e power minus 1 by 2 sigma naught square xi minus mu1 whole square, then minus this term, right? This is greater than k1. Then we will expand this term. We can write this term, it is e power minus 1 by 2 sigma naught square. We will expand this term, that is summation I 1 to n here. What is a minus b whole square? That is here in the case xi minus mu1 whole square, which means summation here, summation, right? Then xi square plus summation I1 to n, then here mu1, right? Then we can write n mu1 square minus 2 into summation xi and also mu1, right? Then you can write mu1 summation I 1 to n xi 1 to n xi, right? This is the expansion of this term. Then next we will expand this term. What is that? It's also minus summation I 1 to n xi whole square minus n mu naught square plus 2 mu naught summation I 1 to n xi, which is greater than k1, right? Here we will expand it, these two terms, right? Then here this term got cancelled, right? Then we can write this term as e power minus 1 by 2 sigma naught square. Then we will write this term together, that is here n, right? We can take n outside, that is n into mu1 whole square minus mu naught square minus here also 2 into summation xi is common, right? Then we can take outside 2 into summation I 1 to n xi here mu1 minus mu naught, right? Which is greater than k1, which implies e power minus 1 by 2 sigma naught square same, right? Then we will take log on both side. Okay, then take log on both side. Then this term become, here we take log, then which implies that minus 1 by 2 sigma naught square, right, into n mu 1 square minus mu naught square minus 2 summation I 1 to n xi mu 1 minus mu naught, which is greater than k2. K2 means here k2 equal to log of k1, right, because we are taking here log on both side. Then this term is here not e power, right? Here if you are taking log on this term, then we can get minus 1 by 2 sigma naught square, then the common term, and which is greater than k2. That means k2 equal to log of k1. Okay, log of k1. Then we will which implies, what is the last term here, 1 by 2 sigma naught square, right? Then we can take this term here, that is divided by this term. Sorry, we will take this term in here. Okay, then the remaining term is n into mu 1 square minus mu naught square minus 2 summation I 1 to n xi into mu 1 minus mu 2, right, which is greater than k3, because here k3 equal to 2 sigma naught square into k2, right? So we have multiplied there in so here, see here it is minus 1 by 2 sigma naught square, right? Then we can multiply both side by minus 1 by 2 sigma naught square, right? Then here the sign is changes, right? It is less than, because we multiplied by minus 1 by 2. Sorry, we change that, right? Here here minus 1 by 2 sigma naught square, right? Then we can take then you can multiply it by minus 2 sigma 1 by minus 2 sigma naught, sorry. Right, then these sum got cancelled. Then here it's a changes the sign, right? Then this term become n into mu 1 square minus mu naught square minus 2 summation xi mu 1 minus mu naught is less than k3, which means k3 equal to minus 2 sigma naught square into k2. Okay, then which implies you take this term here. Okay, that is minus 2 summation I 1 to n xi mu 1 minus mu naught less than k3. Then this term that is minus n mu 1 square minus mu naught square, right? Which implies that summation I 1 to n xi, which is less than k3 minus n mu 1 square minus mu naught square, which is divided by this remaining term. It is remaining term, that is here minus remaining term means 2 into mu 1 minus mu naught. Then we will take here negative side, we will multiply by minus 1. Okay, then this term become summation I 1 to n xi, which is greater than minus k3 minus n mu1 square minus mu0 square divided by 2 mu1 minus mu0. Okay, so this is the rejection region. That is, rejection region is the summation I 1 to n xi, which is greater than k. Then what is the value of k here? K means this value, right? That is k equal to k3 minus k3 minus n mu1 square minus mu0 square divided by 2 mu1 minus mu0. Right. So here we got the rejection region, right? It's a function of a random variable, right? So we in all cases we need to find out the rejection region in the case of function of a random variable. Here function, right? That is summation xi. So this is the rejection region. Then we can write the most powerful test for testing H0 versus H1. Therefore, most powerful test for testing H0 versus H1 is phi of summation I 1 to n xi equal to 1 if summation xi is greater than k, 0 otherwise. Right, this is the most powerful test for testing H0 versus H1, that is phi of summation xi. This summation xi is founded from here, right? That is 1 if summation xi is greater than k. Right, that means we reject H0 when summation xi is greater than k with probability 1. Right, this is the most powerful test for testing H0 versus H1. So here we need to find out what's the k value, right? So where critical value k can be determined by using size, that is expectation of phi of x and the H0, which is equal to alpha, right? So using size we can find out what is the critical value k. Okay, what is the expectation of phi of x? So here phi of summation xi, right? You can use these function, this summation expectation of phi of summation xi and the H0, which is equal to alpha, that is which implies probability of 1 into probability of summation I 1 to n xi using this most powerful test. 1 into probability of summation xi greater than k plus 0, right? Greater than k plus 0, it's equal to alpha, right? It's equal to probability of summation I 1 to n xi greater than k equal to alpha. So under H0 we know that summation xi follows, under H0 we know that xi follows normal with mean x0 and variance sigma square. Then summation xi follows, here is summation xi, right? Then summation xi follows normal with the mean n mu naught and n sigma naught square distribution, right? So then here we know that summation xi follows normal with the mean n mu naught and variance n sigma naught square, right? Then we can take these terms as a standard normal variable. Then we can convert these random variable as standard normal variable. right? How to convert a random variable, normal random variable to standard normal? That is probability of summation xi minus its mean, right? That is n mu naught divided by its standard deviation, that is n sigma naught square, right? It's greater than k minus its mean divided by its standard deviation is equal to alpha, right? Which implies probability of, this is a standard normal variable, right? Normal variable minus its mean divided by square root of its variance, that means standard normal variable, which is greater than k minus n mu naught divided by square root of n sigma naught square, which is equal to alpha. So here we need to find out the value of k, right? The critical value, which implies then what is the value here? It is k minus n mu naught divided by square root of n sigma naught square equal to, here probability of z value is greater than some term equal to alpha, right? It's greater than, right? Then it's equal to z alpha, right? Now what is k? K equal to n mu naught plus z alpha square root of n sigma naught square, right? So this is the critical value. Okay, so for this value summation xi is greater than this value, then we can reject h naught for with probability 1, right? Here k, right? Then we need to find out what's the power of this test. So we know that in most powerful test, which means size equal to alpha and power is a maximum, right? Then we can say that is the most powerful test. So in the case we have to find out the power of the test also, that is power of the test is beta equal to what's formula? Expectation of phi of summation I1 to n xi and the alternative hypothesis, right? It's equal to probability of summation xi I1 to n is greater than k and the alternative hypothesis. So under alternative hypothesis we know that under h1 x follows normal with mean mu1 and variance sigma naught square, right? Mu1, right? And then summation xi follows normal with n mu1 mean and sigma naught square variance, right? Then here we can convert these standard normal variable into, sorry, these are normal variable into standard normal, that is probability of z is greater than k minus its mean, that is n mu1 divided by square root of n sigma naught square, right? That is power of the test, that is beta equal to probability of z is greater than, here we know that what is k value, right? That is n mu naught plus z alpha into square root of n sigma naught square minus here n mu1 divided by square root of n sigma naught square. This is the power of the test. Okay, in this case we obtain the test. In this case we obtain the power of the test right here. So here first it's given that in this problem we want to construct the most powerful test, right, for testing h0 versus h1. For that we have to use the Neyman-Pearson lemma. We know that from the Neyman-Pearson lemma we reject h0 for the large ratio, that is f1 of x is divided by f0 of x is greater than k, right? That is we have to find out what this value which is greater than k, right? But in here in this case it's given that the size of n, right? Instead of the density we have to take the likelihood function, that is then we wrote likelihood of under h0 and under h1 also. Then we obtain what is the rejection region using likelihood under h1 divided by likelihood under h0 is greater than a value k1. Then substitute that likelihood values, then simplify the terms, then we got the function of random variable. right, which is greater than k, right. So this is the rejection region in that case, in this case. Then then we wrote the most powerful test for testing h0 versus h1, that is phi of summation xi equal to 1 if xi is greater than k, right, 0 otherwise. Then we obtain the critical value k using the size of the test. That is here x follows a normal random variable. X is a normal random variable. Then we transform that into standard normal. Okay. Then we got simplify that term. Then we can write k equal to n mu naught plus z alpha square root of n sigma naught square. Then after we have to find out the power of the test. We know that what is the power. Power means rejectance note under alternative hypothesis, right? That is expectation of phi of summation xi under alternative. Is here similar, right? Because expectation of phi of summation xi, which means probability of summation xi greater than k into 1 0 plus 0, right? See, then here also is a, it follows normal random variable. Then we can transform it as standard normal. So here substitute the value of k obtained from here. So this is the problem. So this is the most powerful test for testing h0 versus h1 in this case. Okay.